All right, people, how are we doing? I'm squeaking these in between conferences. So probably at some point there will be a beep beep and I'll have to go. But don't worry, I'll be back. Here we go. Chapter 10.1. Now we're only doing the first part of 10.1. 10.1 has a couple things in it. So we're only doing the first part, which is the comparing two proportions part. Okay. So for 10.1 and 10.2, we're only doing the first half of each of those chapters. The second half will be a surprise for you later. So exciting. All right. So what we're doing here now, what we've done before is one sample confidence intervals. What we're going to do now is two sample confidence intervals. Okay. So we're going to be able to compare two proportions to each other, right? So we have eighth graders do something. We find the percent of them who like to do something, and we compare it to seniors, and we find their percentage, and we're seeing the difference between the two. That's the idea. So when we did one sample, so a one prop Z interval, we had these conditions: randomness, independence, and nearly normal, right? Randomness is random sample. Independence is our 10% rule. So I don't like the way we do this here. I like 10n less than the population. Maybe I'll change that in your notes. Probably not. I probably didn't change it. So sorry. But we can change it here. 10n less than the population. And then nearly normal, which is our NP and N1 minus P, or successes and failures greater than or equal to 10. Either way is perfectly fine. Okie dokies. Now that we have two samples, some things are going to change, right? So for randomness, they both need to be randomly selected. Okay. I'm going to skip this one because it's new and scary. But my independence rule is both of my samples must have 10 and less than the population. So I have to check both. Guess what for nearly normal? Both have to pass that. So sometimes you'll see it written N1, P1, and N1, 1 minus P1 are greater than or equal to 10, and then N2, P2, and N2, 1 minus P2 are greater than or equal to 10. Sometimes you'll see it written like that, but we have to check both of them for nearly normal. Okie dokie. So that's kind of the same thing we did before, but now we have two samples, so we just have to check both. Easy peasy. Second thing we have to have is independence between groups. Okay. Basically, the way I look at it is this: it is not paired data. Okay, the data is not paired. It's not one person doing something twice. Think about matched pairs, right? A matched pairs experiment. One person doing something twice, or two similar people both getting both treatments, right? So no paired data. The data should not relate to the other side of the data. Okay, dokie. And usually that's just a statement you make. Assume independence between both groups and you're fine. Cool. All right. Sampling distribution, shape approximately normal. Same, same over here, right? When we subtract them, they should be approximately normal. Sometimes you get um, a little something, but as sample size increases, we get a fairly normal sampling distribution. The center, and I'm going to bring out our beautiful green sheet right here. Again, they have an entire page devoted to sampling distributions, right? This whole page is sampling distributions. So let's find two proportions. Do you see it? Yeah, it's right here. So for two population proportions right there, and we're looking for the parameters, right? So the mean of the center of the distribution is right here. So the mean of the two sample proportions in the population should equal the true mean, or sorry, my bad. The sampling distribution of the difference between the two sample proportions should be equal to the true difference proportions, right? So remember, P can be replaced by pi, right? On this sheet, it's not. I would prefer them go to pi. They're not going to right now, but you can write pi. It's totally acceptable. Um, so the difference in the population should be the same as the mean of our differences from the sampling distribution. Okay, so we can write that here. So the center of the differences of our sampling distribution should equal the difference between, do we do 2 minus 1, 1 minus? I'll do exactly what's in there. is the difference of the true difference between the two, right? Cool. The spread before was this P times 1 minus P over N. It gets a little nasty here. Okay, it gets a little nasty. So we're going to write this in the standard deviation of the sample proportion difference is, and it's still a big old square root, okay? But we're going to take our P1 times 1 minus P1 and put that over our sample size 1. And guess what we're going to do over here? We're going to do the same thing for the other, right? Just like that. Okay. For standard error, this is the standard deviation. For standard error, remember, is just standard deviation of the sampling using sample statistics. Replace P with P hat. So P hat 1 minus P hat 1, right? P hat 2, right? So we just replace that and we get the sample standard deviation, right? So that would be S of P hat minus P hat equals, and we do the same thing except with the hats on it. Okay, dokie. You're never really going to have to do, again, the only time you would use this is a multiple choice question. What is the spread of this situation? And they give you 5 of these, all slightly different, right? Okay. Um, there is one thing I want to show you here. And we're not really using this now. We'll probably talk about this later. So here's our standard deviation. Here's our standard error. You see, basically the same thing on the green sheet, right? If we assume the two proportions are equal, and we'll be doing this later, we change things. We pool our data together. Okay, so I will allow you to write pooled on it. It is never wrong not to pool. It's okay not to pool. If you're not sure, like, should I pool or not? Don't pool. Okay, never pool if you are not 100% sure you should pool. And we'll talk about what that means when we get back to this later on. For now, don't worry about it. Use this. Okay, always use this or this. Cuckoo. All right. To create a confidence interval, we're trucking along here. To do a confidence interval, right, we check our conditions, assumptions, then we name it, do it. It's a two sample Z interval for a difference of proportions, right? Or we could call it a two prop Z interval. That's what your calculator will call it. Okay. We find that in stat calc tests. Is that right? Stat calc. Oh no, stat. My bad. Stat test. Stat test and then two prop z. Okay, that's where you find it. Okay, the test formula is going to be the difference between the two proportions. Okay, so P hat 1 minus P hat 2. Okay, that is our estimate of the difference, right? So we could do that. Plus or minus our Z star times our standard error or standard deviation up here, whichever one we have. Sometimes we're given the population proportion and then we use it, and that's fine. If we're not given the population proportion, we replace it with P hat, right? Our sample proportion, and that's fine too. Okay, so we go with P2, 1 minus P2 all over N2. Cool. There we go. All right. All right. Again, formulas, you can do it by hand, but you're not going to have to. We're going to see that on the next side. Are we ready? Here we go. Here's our example. Just jump right in. A large company has two shifts, a day shift and a night shift. Ooh, parts produced by two shifts must meet the same specifications. The manager of the company believes there's a difference in the proportion of parts produced within specs by the two shifts. Thinks one group is doing better than the other, wants to find out. To investigate this belief, random samples of parts that were produced, there's random, I liked that word, were produced on each of these shifts were selected. For the day shift, 188 out of 200. So I'm going to do P hat day for day shift is 188 out of 200. I just like to write these down just because I know I'm going to use them. For the night shift, so P hat night, I could do D and N is fine, but I wrote it out so it looked better. 180 out of 200 parts met the specifications. Use a 96% confidence interval to estimate the difference in proportions of parts produced within specifications by the two shifts. All right, so here we go. Are you ready? First step, we're going to do conditions and assumptions. So we want to talk about randomness. Was there randomness? Yes, it was stated. Stated that they were random samples. I might even draw a little thing up there. So that one's good. We got randomness. Um, let's go nearly normal. Okay. We need successes and failures for both greater than or equal to 10. So success and failures for day shift and success and failures for night shift, both greater than or equal to 10. Okay, so we need to prove that. Success for the day shift was 188. Failures would be 12. Success for night shift is 100. Oops, sorry, is 188. I was looking ahead. Sorry, that's an 8, 8, 8, 188. Oh, it doesn't look any better. 188. All right. And then here we got 180 and 20. All of these greater than or equal to 10. All these there. You could find the proportion and then multiply by 200. You're going to get the same exact number. So that's why I like success and failures, especially in instances like this. So there we go. Nearly normal is looking good. Independence, 10% rule is my 10 times the sample size should be less than the population, right? For both, right? So we need at least, safe to assume, greater than 2,000 parts for both shifts. Does that sound reasonable? I think so. I think so. So independence 10% rule, check. I'll just kind of highlight all these like this, show that we checked them all. And the last one is independence between the two groups. And here I just usually use a blanket statement. I'd say safe to assume these two groups are independent. Some of you would be like, well, what if, what if, what if, what if? No, just stop doing the what ifs, right? Just unless there's a compelling reason why, right? Just go with it, right? Don't borrow trouble here, people. Don't borrow trouble. All right, here we go. We're going to name it, do it. Name it, do it. Okay. This is called a two prop Z interval. Okay. I'm going to show you the easy way to do this. We're going to grab our calculator. We're going to turn it on. We're going to ignore the battery is too low. We're going to go stat. We're going to go to tests and we're going to go to 2 prop Z int, which is down a ways. And it's going to say group one, successes and total number. So 188 and 200. Oh, see, I told you it would go ding, ding. All right, I'm going to pause. All right, here we go. I'm back. It was a good conference. Oh my gosh. I don't know if the name pops up. I better check that. I better check and make sure. Um, but it was good. So if you saw the name, you're like, oh, okay. Everything was cool. Everything was cool. All right, here we go. Where am I? Oh, name it, do it. And I was grabbing my calculator to actually do it. My calculator was low. Let's go back to it. So stat test, I'm going down to 2 prop Z interval, not test. Um, Tests are coming soon. That's the other half of chapter. We're going to do tests later on. Don't worry about it now. Don't freak out. You're like, tests, that sounds scary. It's really not. They're actually really fun. Um, oh my gosh, another person. I think they're early. All right. Well, I got this in. I'm just going to go quickly to calculate and we're going to write this down so we have it. Ready? Was it nine? Oh, it said 96% confidence interval. So I need to change that to a 0.96 and press calculate. Let's write this down before I go to that conference. All right. Negative. That's important. 0.0156 comma positive on this one, 0.095. I'm going to just write the whole thing down, 557. Good. There we go. We'll come back in a second after this conference. This will be a good one too. I love all my conferences. They're good times. So here we go. Pausing and see you in a little bit. All right, here we go. I told you that was a good one. That was a good one. Again, I need to check and see if the names show up. Maybe I can blur them out. You'll be like, oh, that person, I know that person. Well, they're awesome. Good job. All right, here we go. So this is an AP exam, and this is the question that they ask. This is all you need to do. Keep it super simple. You don't need to use the formula. We're going to show you how to use that in a second. If this is an AP exam, I would go right to interpreting, right? Or interpret. I don't know. I wrote the ing. All right, here we go. So we're going to say we are, and in this case, we're 96% confident, 96% confident that the true difference between what is it, night and day? Do we do day and night? Between day and night. Oops, not getting it on the screen. Shift. Um, Day and night shift. Proportion of parts. It's not really reading very well. It's okay. It's okay. I'm getting the context in. Proportion of parts within specs. Difference is between negative 0.0156 and positive 0.09557. Boom. Awkward. Does not sound good to me at all as I read that, but I got the right things in. I got how confident I am. I got the context, true difference between these. And then I said the difference is between these two. I might do, because this is day minus night, sometimes that's important. So I did day minus night, right? And I think it says shows that on my calculator when I get there. Again, it's doing that thing, stat test, um, and then calculate 96%. Okay, good. Oh, it doesn't. Oh, it doesn't. Okay, whatever. But it does show you the proportion differences, right? So one was 94%, one was 90. So P1, it is P1 or P hat 1 minus P hat 2, right? The average difference, the middle of this confidence interval would be 0.04, right? And we're going about 5.5 above and 5.5 down. So you could find the margin of error that way. All right. Speaking of, if you're doing this by hand, right? You would have the formula P hat 1, which would be day, minus P hat night. And then we would add or subtract our Z star times the standard error or standard deviation of the sampling distribution. All right, so I do know that this was 0.94 minus 0.90 for that plus or minus. Now I need to find my Z star for 96%. Ooh, is that on here? Yeah, oh, it is. Thank goodness. Oh, I was like, oh my gosh, maybe it's not on there. I have to use. All right, so there's 96%. And for Z's, we just go up one, right? So 2.054, 2.054. And then if I was plugging in, and again, you're not going to have to do this by hand if it's here. If it's a multiple choice question, you might need to plug stuff in. Okay, so I'm going to go P hat 1, which is 0.94. The order doesn't actually matter in here because we're adding the two fractions together, right? Um, and they're both over 200. So this is 0.94 times 0.06. This is 0.90, right, times 0.10. And there we go. And if you figured all this math out and you added this, you would get this. And if you subtracted this, you would get this, right? It's going to lead to the same things and the same interpretation. But it is good to know how to do this and do it once in a while, maybe, because it could be, hey, what is the confidence interval for this problem? This. Five choices, choose the right one. And they like mess with this number or they mess with these or these, right? They do some weird stuff, right? So you're looking for, can you use the formula correctly? Do you understand the formula? Okay, cool, cool. There we go. And last thing, we're going to do part B, based only on this confidence interval. So only looking at this. Do you think that the difference in proportions of parts produced within specifications by the two shift is significantly different from zero? Okay, so is it significantly different from zero? Remember that an interval is what we think is a feasible value. Okay, so looking in here, it's asking about the number zero. Is zero a feasible value? Is zero in there? Yes. So I'm going to start this off by saying zero is within our 96% confidence interval. Therefore, it is a feasible, um, uh, feasible. All right. Again, when I don't know how to write something, if is it an A or an I think it was an I get confused with the spelling. It's okay. Just make it kind of messy, right? And then keep going. Giving you so many good tricks here. Therefore, it is a feasible difference. So based only on this concept, do you think the difference proportion parts within there we go. There's not significant evidence of a difference between the two shifts. Even though it was 94% to 90%, it's still within reason that they are producing about the same accuracy level. Again, I use the word accuracy, but they're producing at about the same meet specs level of stuff. Cool, cool. And that's it. We got some additional practice for you. And you know how this works by now. Press pause or bounce or just follow along. You know what to do. Recent study reported that a sample of 248 women, 58 had changed their political affiliation since the last election. All right, so P hat for women is 58 out of 248. It is also reported that 120 in a random sample of 387 men had changed their political affiliation. So P hat men is equal to 120 out of 387. The researchers would like to know if these data provide convincing evidence that the proportion changing political affiliation is greater for men than women. Is it greater for men than women? Okay, so we're going to answer that down here. So the first step is just to create and interpret a 95% confidence interval. Let's do it. My head's like up into this. So, I'm so sorry about that. Oh, I'm losing it here. Here we go. Conditions, assumptions. I'm going to do these pretty quickly. Is there some kind of randomness? And it is stated up above. I can see it. I'm just going to say it. Boom. Random sample, two random samples. Okay. Is there nearly normal? Normal means successes and failures for both groups. Both groups need to be greater than or equal to 10. Again, this could be NP and N1 minus P for both groups. I like successes and failures, makes it easy. We've got 58 and 190 for women. 58 successes. This minus 58 is 190. That's how I got that. 58, 190. Here we've got 120, and this minus 120 is 267, all greater than or equal to 10. So success, failure, right? All right, good stuff. So nearly normal, we are good. 10% rule, so 10n less than or equal to the population. I know that there are at least 2,480. Is this just voters, women voters, potentially? I guess so. 2,480 female voters, women voters. and at least 3,870 male voters. I'm going to write assume or safe to assume. So I like that one. That one's good. So safe to assume at least 2,480. I just multiplied that by 10, right? 10 times. Our population needs to be big enough to support the samples of these two sizes, right? So we got to multiply by 10, and that's the minimum of the population size. Okay, you remember that. Independent samples. So independence between, again, blanket statement. Assume these are two independent samples. Okay. Pretty good. I mean, they're different sample sizes. If they were both 248 and maybe they were married couples, right? And they got the female in the married couple and the male in the married couple, and maybe they're not independent, right? Maybe, people who are married to each other have the same political I don't know, right? So that would be kind of a paired thingy, right? So basically, is it not matched pairs? This is not matched pairs, not even the same size, right? All right. Name it, do it. Name it, do it. Here we go. Let's do it. This is going to be a two prop Z interval calculator on yes, you're running out of battery. How long will you last? Two prop Z interval, and I'm going to put in 58 out of 248, and I'm going to put in 120 out of 387, and our confidence level is 95%. Always check that. It's easy to forget to change it. Ooh, exciting. There we go. All right, our confidence is negative 0.1462 and negative 0.0062. Oh, it almost gets to zero, but doesn't quite get there. All right, interpret. Interpret. We are 95%. It was 95%, double check, confident that the true difference, and I'm going to go, I think we had women as the first one, women minus men. The true difference of proportions of people changing political parties. Ew, parties. My writing's getting worse. Is between negative 0.146 and negative 0.006, right? There we go. So what does that mean, right? That means females were pretty sure when we compare those two percentages, right, we're pretty sure that females were somewhere between 14% and about 1% below the males. Does that make sense? So males were between 1 and about 15% more likely to change parties. Okay, that's what this means, right? So interpreting this sometimes can be tricky. You can always just do it this way, right, using these numbers, but it's also a good idea to kind of know what's happening, right? That's what this means because it was women minus men. And if it's negative, that means the men were higher. Does that make sense? Okay. Using only your interval above, is there significant statistical evidence that the proportion changing political affiliation is greater for men than women? Okay. So important number is zero. Zero is not included in the interval. So this is showing that there's a difference, right? What we need to talk about, though, is the difference could be on one side or the other. Okay. So we need to figure out which way it's going. All right. So zero is not in the interval, and it is above the right bound. Okay. Or the entire interval is negative would be another way to put it, right? Sometimes the entire interval would be positive. What does that tell you? Okay. So that would not be a bad way to say it, right? The entire interval is negative, showing that all feasible values have women lower than men in terms of the percentage, right? Um, Evidence that women percentage changing political parties is likely, never commit, likely lower. Cool. There we, oh gosh, that wasn't, I thought I saw it. Sorry. So zero is not in the interval and it is above the right bound. This is evidence that women's percentage changing political parties is likely lower. If you said both, lower and upper, or both, our entire interval is negative, and that gives evidence that women were lower than men in terms of changing political affiliation, that would be great too. Okay. But don't just say that zero is not in the interval because that's not enough, right? It's also the direction that it's not in the interval that matters. Cool, cool. All right, people, that's it. We'll see ya. Woo!